Alrighty, ladies and gentlemen, this is 4.2 part B. We're going to be wrapping up our examples with the U-sub method. So I think we're just going to do 4 final examples that are a little bit trickier than the first 4 that we looked at, but all utilizing the U-sub method to perform an antidifferentiation or integral. So let's jump right in. If you have not watched 4.2a, you should go back. So go back now and do so. Okay, share screen, advanced. Okay, content camera. There we go. So the idea with the U-sub method is it's kind of like a reverse chain rule. When we're looking at a function that we're trying to find the antiderivative of, and it seems like a product of a composite and potentially its derivative, and kind of undoing that process. And what we've been doing is defining a u, substituting that in, and then substituting out the dx. And the way that I've shown you is to solve explicitly for what dx is. And in most cases, with the u-sub method, we have a nice canceling out when the dx gets subbed out. For the du expression, the leftover x's or extraneous variable end up canceling out, and we're able to integrate or antidifferentiate just in terms of u. Well, with our very first example today, example 5, we're going to see that sometimes it doesn't work out quite that smoothly, and that we'll have to do kind of some further finagling in order to find that antiderivative. So by that I mean something like example 5. And we're going to kind of do additional tailing here. When u-sub doesn't work. And I'm putting that in quotes because what we're going to see is it actually does work. It just requires an additional step. We will eventually get some integration problems where u-sub really doesn't work, and we have other methods to find those integrals. So when u-sub doesn't work, quote, quote. And so perhaps we were looking at something like the antiderivative of x squared times the square root of 1 plus x dx. And if we're kind of following the general strategy that I've been telling you, is that we should usually choose u to be the innermost part, okay? Because with u-sub, there's almost always going to be some sort of composite situation going on. And so we're going to go into the innermost function and call that our u. So in this case, the innermost function will be 1 plus x, because it's kind of encased in this outer square root function. And so we'll say that u is equal to 1 plus x, which means that du is equal to just dx, because the derivative of this guy on the right is just 1. So du dx is 1. We multiply by the dx to get du is dx. Row. Because now, let's see if I want to do this. If we go and do our subs, we don't get that magic moment. This magic moment. Anyway, what we end up with is x squared times, we'll call this u to the 1/2 du. Subbed in the u, subbed out the dx. But usually when we do this sub out of the dx, there's some other part of this expression that nicely cancels the remaining thing. That ain't happening here. So, row. So what the problem here is x variable doesn't cancel. So we're going to make it cancel, or rather we're going to just force it out of there. Redefine it. What? Well, we defined u as some expression in terms of x, so it stands to reason that we can rearrange this definition to be a definition of x in terms of u. So some little trickeration going on here. We said that u is equal to 1 plus x, which means that x must be equal to u minus 1. And now we have a way to make this antiderivative only in terms of u by simply substituting in u minus 1 for x. So yeah, it will require a little more work. It won't be quite as smooth as we're used to, but it will be something that we can find the antiderivative of. So we're going to write this as not x squared now, but u minus 1 squared times u to the 1/2 du. Now, of course, we have some expansion that needs to happen here and then some distribution. So we just have to be careful here and remember our algebra 1. This will be the antiderivative of u squared minus 2u plus 1 times u to the 1/2 du. Doing this distribution now with the u to the 1/2, we get the antiderivative of u squared times u to the 1/2 is u to the 5/2. That could be a potential oopsie. Remember, when we're multiplying the bases, we add the exponents, okay? I'm sure that somebody's first instinct was to say that u squared times u to the 1/2 was u to the first. So there's going to be u to the 5/2 minus 2u to the 3/2 plus u to the 1/2. And to be totally honest, that was my first instinct as well. I haven't had my full cup of coffee yet. I didn't really sleep much last night, so bottoms up. Baby girl just freaked out last night. No reason. Took the bottle for like 5 minutes, and then I burped her, and then she just started losing her mind. Every time I tried to give her the bottle, she would just, and then start freaking out again. So, yeah. Parenthood, man. Good stuff. But she and Mama are at a doctor's appointment right now, so Daddy's got the house to himself, and what's he doing? Recording a calculus lecture. All right, enough about me. Let's integrate this. So yeah, like a little bit nastier now, but this is just, a sum and difference of power expressions, and we can apply the technique from 4.1 to come up with this and then sub back in for u. So the antiderivative of u to the 5/2 is u to the 7/2 over 7/2. The antiderivative of u to the 3/2 is u to the 5/2 over 5/2. And the antiderivative of u to the 1/2 is u to the 3/2 over 3/2. And then cleaning this up a little bit. Oh, and then I almost forgot, plus c. Making this look pretty, we get 2/7 u to the 2/7, sorry, 7/2, minus 4/5 u to the 5/2, plus 2/3 u to the 3 halves plus c. And then bringing it on home, we need to sub back in for u. So we get 2/7. U was 1 plus x. 7 halves minus 4/5, 1 plus x to the 5 halves plus 2/3, 1 plus x to the 3 halves plus c. Okay. So that is the way that we can sort of force a u sub if we ever get to a roadblock like this, okay, where subbing out dx does not create that magic moment that gives us just an expression of u. Sometimes we have to go this extra step to define that initial variable in terms of u so that we can do the integration. We're not going to check this one. It's kind of more trouble than it's worth. Okay. So now, example 6. I believe the rest of these, they all work. I don't think there's any more where we're doing this other definition, but these are just a little bit trickier. There's some trig stuff in here, and just stuff we need to be careful of. So we'll kind of go carefully through these, but these should all be pretty straightforward in terms of the mechanics of how the u sub work. None of these more trickeration ones. So for example 6, we are looking at the integral of sine of the square root of x divided by the square root of x dx. Okay, which is a little bit concerning because this is a quotient and not a product, which we haven't done a whole lot with. But as we'll see in a second, it will probably behoove us to think of this as x to the negative 1/2. Maybe we can do that. No, we're going to leave it like that. For now, we're just going to define our u, kind of using that same notion of looking for the innermost function. We have a composite function involving sine, sine being the outer function, square root of x being the inner function. So we're going to say that u is equal to x to the 1/2, square root of x. Which means that the derivative of u is equal to 1/2 x to the negative 1/2, which means that du is equal to 1/2 x to the negative 1/2 dx. And as our habit is to actually solve for dx explicitly, that means that dx, and we gotta be careful here, we're dividing both sides by 1/2 x to the negative 1/2, which means that this is going to be equal to 2x to the 1/2 du. Okay. When we have a 1/2 x to the negative 1/2 in the denominator, we flip those into the numerator and make them 2 and x to the 1/2. So going back to our integral, so like this, I know I went through that kind of quickly. This is probably the tricky part of the problem, is that the u sub gives us this rational exponent expression, and having to rearrange this, that's sort of the tricky part. I think once we plug it in, you'll kind of say, like, oh, that wasn't that bad. Okay, and so doing our u sub and subbing out for dx, we end up with the sine of u over the square root of x. Dx is twice x to the 1/2 du. You might be thinking, Mr. Smith, that doesn't really look like the magic moment. No, but it is, because remember, x to the 1/2 is the square root of x. Those two cancel. Okay, another way to think about this is if we wrote this one here as x to the negative 1/2, when you multiply x to the negative 1/2 times x to the positive 1/2, what do you get? Well, you get x to the 0 power, which is just 1. So these do indeed cancel out. And so now we're looking at a much, much, much friendlier 2 times the antiderivative of sine of u du. Okay. So the tricky part of this problem was all in here. Once this is all done, this is a very straightforward integral. This turns into twice the opposite of the cosine of u plus c. And then subbing back in for u, we get negative 2 times the cosine of the square root of x plus c. I'm not going to show it, but if you are incredulous that this is correct, just differentiate it and you'll get back this. All right, halfway, 2 more to go. Example 7. What's going on in example 7? I guess just kind of a what do I choose type situation. But we're okay. This one's not too bad. So we're going to have the antiderivative of the sine of x times the square root of 1 minus the cosine of x dx. So there might be a brief moment of hesitation where you're thinking, well, which one do I choose as my u? Again, kind of just looking for the innermost situation. I'm thinking 1 minus cosine of x because it's sort of encased within, composed within the square root. We'll see in example 8 that especially with trig functions, you can sometimes get away with choosing either one. But for this one, we're going to choose kind of the obvious 1 minus cosine. So u is equal to 1 minus cosine. So du then is so the derivative of cosine is negative sine, which means that with this negative out front, this becomes positive sine times dx, which means that dx is equal to du divided by the sine. So then moving on back over here, we can rewrite this as the integral of the sine of x times u to the 1/2. Dx we just said was du over sine of x. Magic moment, the signs go away. And now this antiderivative is solely in terms of u, namely u to the 1/2. And we know that that antiderivative should be u to the 3/2 over 3/2 plus c, which is really 2/3 u to the 3/2 plus c. And then substituting back in for u, we get 2/3 1 minus the cosine of x to the 3/2 plus c. And once again, if you aren't fully trusting that this is correct, take this derivative and you'll end up with this. Okay? Kind of verbally, you can just see, like, we'll use the chain rule here. The 3/2 from the power rule will cancel with this 2/3, leaving us with a 1/2 as our exponent. So there's our square root of 1 minus cosine of x. But then chain rule says pop out the inner function, and take the derivative. The derivative of 1 minus cosine of x is sine of x, and we get back here. Okay, last one. And this one's, you know, tricky, but we'll be okay. Ejemplo numero 8. We're going to call this a trig problem 2 ways. We'll say a trig integral. Get used to that word. A trig integral 2 ways. The book has not yet dropped this word integral on you, but that is what we will very soon be using to refer to antiderivatives. So a trig integral 2 ways. And so the integral in question is tangent of x times secant squared x dx. Okay. Now, if we're sort of following our choose the innermost function here method, and it might help to write this as tangent of x times secant of x squared dx. Hopefully the obvious definition to you would be secant of x, because that is clearly inside of a composite function, is the innermost function, where the outermost function is this square function. Okay. But what we'll see, and we'll do this both ways, is that it would actually yield an appropriate answer to use the tangent as our u. Okay. But let's start with what to me seems the obvious choice, which is the secant. And so we'll say that we'll call this A. Option 1. Letting u equal the secant, that means that du is equal to the secant tangent dx, which means that dx is equal to du divided by the secant tangent. So taking that and subbing in, our integral becomes tangent of x. And I mean, there is a tricky bit right here. I will grant you that. Okay, because here's where it could get a little tricky. If we're just kind of blindly following the method, we would turn this into u squared, and then dx becomes du over the secant tangent. And then we would be like halfway magic here. We would see that the tangents cancel. But then we kind of be like, we still got this sort of uncomfortable secant of x floating around. But that's where we gotta like keep our brains open a little bit and not just blindly follow the protocol. U squared, what was u? Oh, it was the secant. So really, we can write this as the secant of x times u du over the secant of x. That secant will in fact cancel. Cool. And so now this is a very straightforward integral. The antiderivative of u du, which is u squared over 2 plus c. Setting back in for u, we get secant squared x, half of that, plus c. Cool. Cool, cool, cool. All right. So what if we were being contrarian, or we just were being somewhat careless and we used tangent for u instead? What would happen then? And the reason we're doing this is to show that sometimes you can be flexible with your choice of u, but also to illustrate a point at the end about the nature of antiderivatives, okay? That sometimes they look different and yet they are valid. And we'll show that in just a second. So the second option, and let's maybe call this, we just use u, but we can really use any variable we want. So let's maybe use v here. Maybe we said v was equal to the tangent of x, which means that dv is equal to the secant squared x dx, which means that dx was equal to the dv divided by secant squared x. So then our integral becomes tangent of x becomes v, secant squared x for now is left alone, and dx gets subbed out with dv over secant squared. And we have our immediate magic moment. Boom, boom. And so we get v dv. Again, basically, not basically, the identical integrals we ended up with here, but there's a bit of a spidey sense in your brain that's going to make you uncomfortable here. Because yeah, we'll integrate this and get v squared over 2 plus c, which, yeah, clearly it agrees. But now when we go to the u sub, or the v sub in this situation, we're subbing in tangent instead of secant. So this turns into the tangent squared x over 2 plus c. What's going on, Mr. Smith? Not the same. Am I lying to you? Does this not work? I mean, it doesn't feel like we broke any rules here. It seemed like it worked pretty smoothly. We redefined, we differentiated, we subbed, we integrated, but secant squared is not the same as tangent squared. So how can these both be the antiderivative to that expression? Well, it goes back to the nature of antiderivatives, that a function can have multiple different antiderivatives, so long as both of them, when you differentiate, get you back to that starting function. And it gets kind of complicated, or appears to be more complicated sometimes with trig functions. With our polynomial situations, they were easy, okay? Because they looked so similar except for a constant. Because of the kind of interrelated nature of many of our trig functions, it's not always going to be that obvious. And so I think probably the most direct way to show this is we're just going to differentiate both of these things and make sure that they both end up with tangent of x times secant squared x. Okay. There's also a way to show analytically that 1/2 secant squared x plus c is equal to 1/2 tangent squared x plus c, which is interesting. Okay. Should we do it that way? No, let's just. So the question is, do they yield same derivative? So for A, we would take dx of 1/2 secant of x squared plus c. And for B, we're going to take dx of 1/2 tangent of x squared plus c. Sorry, wifey is texting. That is an important thing to check on their way home. Beautiful. Okay, so let's differentiate. We'll have chain rule happening. The outer function will pop that down. 2 times 1/2 times secant of x. The 2 just becomes a 1. Chain rule says take the derivative of this inner function. The derivative of the secant is the secant tangent. The derivative of c is just 0. The 2 and the 1/2 cancel, and we end up with secant squared x times the tangent. So that one works. That gets us back to where we started. Now let's see if this one works. Same, for very similar mechanics here with the chain rule. With the power rule, to drop down to 2 times 1/2 times the tangent of x. That becomes a 1. And then the derivative, or the chain rule, tells us to take the derivative of this inner function. The derivative of the tangent is the secant squared. The derivative of c is 0. The 2 and the 1/2 cancel, and we end up with tangent x times secant squared x. So even though these two antiderivatives are different, they yield the same derivative, and so they both act as valid antiderivatives to our function, to our starting expression up here. Okay, so that's kind of the tricky nature, or can be the tricky nature of integrals. There are usually multiple, or there are always multiple functions that can serve as an antiderivative to a particular function. Remember, the other way is not that way. There is one derivative for each function, just one. But in the opposite direction, there are multiples. Okay, so that wraps up 4.2. We will see you next week.